So today we are going to discuss a very important topic related with the design of distillation column. The one is a concept of number of stages, and the second is the concept of efficiency in the distillation column. So now let us look the first one, that is the number of stages, NS, or the number of trays, that is a NT. So what is the meaning of these two, and what is the relation between the number of stages and number of trays? That is basically here to understand in this lecture. So basically the distillation column, we know that the equilibrium between the vapor and liquid is maintained at each stages, that we have already gone through how to find the number of stages through the Macabethi method. So what happened? These basically vapor liquid equilibrium is maintained in the two different locations in the distillation column. So there are two locations. First is inside the column. Inside the column means here in this one. And the second is at the reboiler. So in the inside the column there are trays or packings. So let us assume that we have a different trays. So basically inside the column on the trays the equilibrium is achieved, and the reboiler, this reboiler means this one. This one is a reboiler. And what is the meaning of reboiler? Due to the partial in the nature. Partial means this reboiler is partially basically this is a liquid that is coming inside the reboiler, and then one portion of this liquid is being vaporized and sent back into the column, and the remaining portion is taken as a liquid, as a bottom product. So we have the vapor and liquid leaving from the reboiler, which are in equilibrium. That's why we can assume that there is one stage here also. Means this is the position where the equilibrium is established. So there are two main locations. One is the reboiler and the second is a column. So the number of stages are total equilibrium points in the distillation column. Total means both. It means all the trays that is available for the equilibrium and the reboiler that is available for the equilibrium. So that's why we have to count all the points of the equilibrium points for the number of stages. So since the reboiler is fixed, means there is only one reboiler. So one equilibrium point is taken as reboiler, and there are other points are taken from the trays. So we can say that number of stages is equal to number of trays plus 1, or the number of trays is equal to number of stages minus 1. So this is a relationship. You should remember this relationship, and that is a very simple one. Let us take the example. If suppose number of stages are 10, it means the number of trays are 10 minus 1, that is a 9. If suppose number of stages are 12.6, as that is possible because we have gone through the Macabethi and we see that that is not always the whole number. Sometimes it is in a fractional value also. So what will be the number of trays? Number of trays will be 12.6 minus 1, that is 11.6. But actually the trays can never be a part and in a fraction way. Always it is in a whole number. So NT is equal to the 12. If you round up the 11.6, it can be a 12 value. So number of trays are 12 in this case. So this is the basic concept of the number of stages and number of trays. What are the differences between the number of stages and number of trays, and how to calculate the number of trays if the stages are given. Now come to the second one, that is the concept of efficiency. So efficiency in basically the distillation column is we are talking about the efficiency of the trays. That is, we are talking about the efficiency within the distillation column. And basically meaning of efficiency is to find out how much efficient our column is performing. And we all know that it is not possible that every tray is giving the 100% performance. So 100% performance, 100% equilibrium. So it means that no tray is maintained at 100% equilibrium. So that's why we have to find out the efficiency, how much is the performance of that particular tray. It can be a 40%, it can be a 50%, if it can be a 60%. Means we are expecting that it is giving the 100%, but actually it is giving the 60%, 40%, 30%, and so on. So how to find out that one? We can go for the concept of efficiency. There are three main type of efficiency in the distillation column. Normally we are going through. One is the overall efficiency, then there are the second name that is called the Murphy tray efficiency, and then the next one is the Murphy point efficiency or the local tray efficiency. So we have three different types of the efficiency. Let us look one by one. Overall efficiency of the tower, that can be defined by E naught. It's a very simple thing. It is a ratio of the number of theoretical trays to the number of actual trays. So what is the meaning of this one? Theoretical trays means the equilibrium trays that we have calculated In the earlier slide, we have discussed about the concept of the number of trays and number of stages. So number of stages means all the equilibrium stages. Number of trays means all the equilibrium trays. That is called the theoretical trays. And number of actual trays that is required for that one. So that gives the efficiency. Normally what happens, number of theoretical trays are calculated and E naught is calculated, so we can find the number of actual trays. So if we need to find the number of actual trays, it's very simple. You have to divide the theoretical trays divided by the efficiency. That gives the actual trays. So how to find the E naught, that is the overall efficiency? So we have a different correlations. One of very famous correlations is Rickman and Bradford correlation. Although there are so many other correlations are available in the literature. So this is a very simple one where E naught can be calculated as 19.2 minus 57.8 log of UL, where E naught is given always given in the percentage. If we count it, if you calculate it, you will find it is in the percentage, and mu L is the viscosity of the liquid in the centipoise. So this is the equation. You all should remember this equation to find out the efficiency, and this equation correlation is a Drechmer and Bradford correlation. Now let us take a simple example of the efficiency. Calculate the actual number of trays. So we have to find the actual number of trays. If the theoretical number of trays is 7 and the efficiency is 44, so very easy. You have to just divide it. So what it means that 7 upon, you have to put 0.44. 0.44. Sorry. This that gives roughly 50.91. You can say the number of actual trays are 16 number of actual trays are required. Some other example, calculate the overall efficiency of column using the Drechman-Bradford correlation if the viscosity of the mixture is 0.6. So here the viscosity is there given here. You can easily find out with the help of the correlations that we know, that we have just discussed here. Cp is given, only the Cp is the unknown parameter, and you can find out the overall efficiency that comes around 32%. So this is a basic example of the overall efficiency. Now come to the next type of efficiency, that is called the Murphy tray efficiency. The name suggests that it is related with the individual tray, a single tray. For example, this is a tray, that is the nth tray we are taking in general format. What happens if any vapor is coming into the tray, that is a yn plus 1, that is the incoming vapor having the yn plus 1 composition. So then what happens, this is the leaving the tray from the nth tray yn star, and this is the composition of yn star, means the theoretical composition of vapor that is leaving the nth tray. Means if suppose the tray is 100% efficient, then the vapor leaving from this tray is in equilibrium with the liquid available on the tray. So that is called a theoretical composition. Obviously it is not possible. So what happened, the actual composition that is leaving from the tray is yn, that is the actual compositions. So we have a difference between the actual composition and the theoretical composition. So to calculate the efficiency, if these compositions are given, you can find out yn, that is minus yn plus 1, difference between these two values divided by the difference between these two values. So this is the theoretical, this is basically the actual values. So we can find in this way the Murphy tray efficiency. Let us take an example. For example, 65 mole percent yn plus 1 is there, and if it would be taken as a yn star is the equilibrium, and it can be a 75 mole percent, but actually it is not 75, it is a 70 mole percent. So what will be the equilibrium? So take the difference between these two values, 70 minus 65, that gives the value 5 upon that gives the value 5 upon 10. So it comes to be 0.5, that is a 50%. So we can say that in this case 50% efficiency of the tray is there. Now come to the Murphy point efficiency. It is very much similar to the tray efficiency, but it is at a particular point. So just take again example of a tray, and this example is very much similar, and this is y dash n plus 1. There is the incoming vapor at composition at a fixed point. That is the difference. Fixed point means at this point this is a composition, that this composition is not, may not be the entire composition of the column. It can be a very specific composition at that particular point, and this is a composition of the vapor, theoretical composition or equilibrium composition of vapor leaving from the nth tray at a very fixed point. And if suppose it is not 100% efficient, then what would be the vapor composition, this would be the vapor composition yn y dash n, that is the actual composition of the vapor living at that fixed point. So if we know all these three values, we can find the efficiency as in the case of previous one, yn minus y dash n minus y dash n plus 1 divided by y star n minus y dash n plus 1. So in this way you can find out the Murphy point efficiency. So this is about the different types of efficiency. And same example here, 65 mole percent the vapor is entering, and if suppose it is working as an equilibrium point, then it can be 100% equilibrium, then it can be a 70%, 75%, and if it is actual, it is a 70%. So we can find out the efficiency is 50% at that point. So if you compare all these efficiencies, means all these true efficiencies, so you will find that for the very small diameter tower, the vapor agitates sufficiently so that the composition is uniform at on the trays. So what happened at that point, the point efficiency will equal to the tray efficiency, because point efficiency is a very special type of, basically on a specific point, and if the composition is same at each and every point, then obviously this point efficiency now will become equal to the tray efficiency. So that's all about the efficiency concept. Thank you very much.